Rocket motors operate on the same principle as do jet engines. Both are rated in terms of thrust rather than horsepower. Both achieve that thrust from the expulsion of exhaust gases from burning fuel. However, that thrust is not the result of those exhaust gases pushing against the air mass of the atmosphere. This is a very common misconception. You have all seen pictures of rocket launchings. And when the rocket seemed to stand on end for some time, you believed it was being held there by the force of the exhaust blasting against the ground. This is not so. Rocket motors operate on the principle of Newton's third law of motion. For every action, there is an equal and opposite reaction. The result would be exactly the same if the rocket were in a perfect vacuum. In fact, one of the reasons rockets are being developed is because they will operate in a vacuum. And since they carry their own oxygen, be able to enter the rarefied atmosphere of outer space and gain freedom from aerodynamic drag. Now let's see how Newton's law applies. First, we'll change this schematic diagram of a rocket to a simple enclosed cylinder and ignite a propellant charge inside it. As the pressures from the burning fuel build up, they are equal in every direction. Being equal, they can't cause motion in any direction because they cancel each other out. However, when we open one end, the action of the gases exhausting at that end sets up a reaction at the other end which acts. But notice, it is not the exhaust stream pushing against anything which causes the thrust. It is the reaction at the other end. The main components of all rocket motors are a combustion chamber and a nozzle. The combustion chamber provides space in which the propellant is burned to produce gases at high pressures. The nozzle, usually of the de Laval type, is attached to the exit end of the combustion chamber. This nozzle is of the converging, diverging type, in which exhaust gases are accelerated, so that in the smallest cross-sectional area, or throat, they attain the local speed of sound. In the diverging section, these gases are further accelerated to supersonic velocities. Close observation of this should give a better understanding of why the rocket does not get its thrust from any impact effect of those exhaust gases. First, let's state clearly that the exhaust gases do push against the air mass. What is important is that this doesn't have any effect on the rocket. Here's why. The impact of the exhaust gases sets up disturbances in the air. Disturbances in gases are sound waves, and therefore must travel at the same speed as sound. Now, if the velocity of the exhaust gases were to remain below the speed of sound, then the disturbances they create could be transmitted back along the gas column to the rocket. But when the exhaust gases reach supersonic speeds, any forces traveling in the opposite direction would have to travel faster than the speed of the exhausting gases in order to have any effect on the rocket. Now, watch this carefully. As pressures build up in all directions, they not only push against the nose wall, but also force gases back out of the nozzle. Thrust is produced by the difference between pressures at the nozzle exit and pressures at the forward end of the combustion chamber. The de Laval type nozzle is designed to make exhaust gases reach supersonic velocities. A further effect of this design is that as velocity of the exhausting gases increases, pressure decreases. The faster those gases are exhausted, the lower the pressures become. In actual operation, the exhaust gas velocities are so great that by the time the gases have reached the outer end of the nozzle, pressure has been reduced to equal that of outside or ambient pressure. The tremendous difference between this pressure and the original high pressure, which still exists at the forward end, is what gives the rocket its thrust and makes it possible for the rocket motor to operate in a vacuum, where, since the ambient pressure would be zero, the difference between nose and nozzle exit pressures would be equal to the absolute combustion chamber pressure. Now, there are many other factors which also affect thrust. It doesn't make any difference in what order they're listed, because they are so interrelated that it's almost impossible to speak of one without mentioning the other. Let's start with combustion chamber volume. Any change in the volume will increase or decrease the combustion chamber pressure. An increase of combustion chamber pressure will increase the temperature of gases, the temperature of the propellant, and increase the propellant burning rate. All of these will, of course, have an effect on the mass rate of flow of gases. A decrease in the nozzle throat area will have the effect of backing up the exhaust gases and thus increasing combustion chamber pressure, causing increased temperature of gases, higher temperature of propellant, faster propellant burning rate, and change in mass rate of flow. No one of them can be varied without affecting the others. So far, we've spoken only of results caused by variations in the physical design of the motor. However, variations in the other factors would cause similar effects. For instance, inhibiting or decreasing the propellant burning rate would decrease combustion chamber pressure, temperature of exhaust gases, the temperature of the propellant, and reduce the mass rate of flow of the exhaust gases. Variations in the fuel to oxidizer ratio could have a similar effect. An increase in the temperature of the propellant, either before igniting or during combustion, will have a definite effect on the temperature of gases, on combustion chamber pressure, propellant burning rate, and mass rate of flow. Ambient pressure has no direct effect upon any of the other factors in this list, but indirectly it affects them all, because a rocket motor must be designed to conform to the ambient pressure of the altitude in which it is going to operate. And efficient rocket motor design must bring all of these factors into correct mathematical balance. This is true whether the motor be of solid or liquid propellant type. Let's consider a solid motor first. Like all rocket motors, it has a combustion chamber and a de Laval type nozzle. The combustion chamber contains a solid propellant charge. The propellant is molded in various shapes depending on the purpose and the dimensions of the combustion chamber, and will vary in size and shape with each different design. To this is added an igniter, which can be located in various positions in the chamber. This is usually a pyrotechnic device consisting of an electric squib, which acts as a primer to set off a larger charge of powder, which in turn ignites the propellant charge. From this point on, the action is just as we've already explained. The high-pressure gases created by the burning propellant, accelerated by the nozzle, act to give the motor thrust. All rocket motors carry both oxidizer and fuel. Both are mixed together in solid propellant grains in such a way that they will remain inert until they're ignited. Fuels most commonly used are asphalt and oil, rubber, or rosin. Oxidizers are usually potassium perchlorate, ammonium perchlorate, sodium, or potassium nitrate. There are some compounds which furnish both fuel and oxidizer, such as nitroglycerin, nitrocellulose, or ammonium picrate. Propellants of this type must be mixed with inhibiting materials so that they will burn rather than detonate. The regular fuel and oxidizer mixtures are frequently restricted too, but only after they've been mixed and molded according to the design purpose of the rockets for which they're intended, when certain surfaces are coated to control burning. These are called restricted burning charges. There are many more shapes, but these three are good examples. They are the star-chambered, the cruciform, and the solid cylindrical. The star-chambered grain has a star-shaped passage running through the length of the charge. It is restricted on the outer surface where it comes in contact with the chamber walls. This design was developed to provide a constant burning area and reduce combustion chamber wall temperature. The cruciform is restricted on two opposite sides of the crossform and each end, leaving a large burning area which will remain constant throughout the burning period. The solid cylindrical grain is ignited at the nozzle end. and is usually coated so as to restrict burning on all surfaces except the nozzle end, and thus has earned the name cigarette burning. Multiple grain and the hollow cylindrical are almost invariably unrestricted and burn on all surfaces simultaneously. Even though most solid propellants will store for short periods, under extreme climatic conditions, such temperature variations will have a definite effect on their amount of thrust and the length of time they will burn. Propellants which are heated before igniting will burn rapidly, giving greater thrust, but shortening the total burning time. Coal propellants, on the other hand, will burn more slowly, giving less thrust, but will burn appreciably longer. Neither of these conditions are liable to create any hazard as long as temperatures are within design limits. However, there is one exception. Propellant grains become brittle in extreme cold and can be fractured if handled carelessly. The danger is that since the propellants are inside the combustion chamber, such a fracture would not be discovered. If this were to happen, when combustion reached the fracture, too large a burning area would be presented, suddenly increasing pressures beyond design limits, and the rocket would blow out. Here is a liquid propellant motor of the bi-propellant type being made ready for firing on a test stand. The lack of clean lines in this rocket is because you are looking at the power plant itself, which in liquid motors is built so that it may be installed in any type vehicle. Although basically the same as a solid motor, the liquid motor has more parts, which are necessary to handle the two propellants. Again, a fuel and an oxidizer, both liquids, that ignite upon contact. The nozzle is identical with the one used in solid motors. The combustion chamber may be smaller, since it doesn't have to store propellant. The injector sprays the two propellants into the combustion chamber. Fuel and oxidizer must be kept apart until they meet in the combustion chamber, so there are two propellant tanks. These are connected to the combustion chamber by a feed system, part of which also acts as a cooling system by carrying one of the propellants around the nozzle and combustion chamber walls. This not only serves to cool the combustion chamber and nozzle, but also heats the propellant to a more efficient temperature for combustion. On this system, two pumps force the propellants through the feed lines, and valves control the propellant flow, making it possible to start and stop the liquid motor at will. Another system utilizes high-pressure gas instead of pumps. There are many variations of these designs using bi-propellants, separate fuels, and oxidizers. The ideal motor would be one that used monopropellants, single compounds containing all components necessary for combustion. It would be much simpler, requiring only one tank, one pump, one valve, and one feed line. The drawback is fuel. Although extensive research is underway, so far we have none that is completely satisfactory. So until we do, we'll continue to work with two tanks, two pumps, two valves, and two feed lines. The propellants used in these motors are called bi-propellants because they consist of two separate liquids. One a fuel, the other an oxidizer, neither of which will burn without the other. Some typical fuels are alcohol, standard petroleum airplane fuels, and aniline. Most commonly used oxidizers are liquid oxygen and nitric acid. Aniline is used only with nitric acid, and this teaming gives excellent performance. Occasionally, nitric acid is used with petroleum and is preferred for some systems. Liquid oxygen may be used with either alcohol or petroleum. Because of its low temperature, less than minus 297 degrees Fahrenheit, liquid oxygen must be stored in thermos containers. But it is a very powerful oxidizer which causes any combustible material to burn rapidly. Used with either alcohol or petroleum, it makes one of the best propellant teams now in use. The extreme low temperature of liquid oxygen makes it very dangerous to handle. It will burn the skin in 10 seconds, and longer contact will freeze the flesh. So it must never be handled unless protective clothing is worn. This is also true of red fuming nitric acid, most often used to oxidize aniline. This acid will not only destroy the flesh, causing burns that are extremely difficult to heal, but its fumes are extremely dangerous and if breathed can cause death. Aniline, while an excellent fuel when used with nitric acid, is highly poisonous. It may be absorbed into the bloodstream through the skin, where it will destroy the red corpuscles and cause anemia. Acute cases of aniline poisoning can cause death. Aside from personal precautions, none of these liquids should be handled carelessly. In loading, only one of any two propellants is handled at one time, never both simultaneously. And care must be taken to dispose of any spillage before the next half of the bi-propellant team is brought to the rocket motor, so that spillage from the second propellant will not cause combustion during the fueling operation. This is especially true of aniline, which has a very low vapor pressure and will therefore contaminate an area for a long period. Alcohol and petroleum are ideal fuels because they are readily available, non-poisonous, they store well, and are comparatively easy to handle. It must always be kept in mind that rocket propellants are capable of unleashing more raw energy than any other known fuels. The devastation which could result from the least carelessness or lack of familiarity with precautionary measures makes it mandatory that no person handle propellants until he's been thoroughly schooled in proper methods and safety procedures. This motor is now fueled and ready for firing. Although an igniter is sometimes used to start combustion, the fuel and oxidizer will usually burn immediately. Burning will then continue as long as the fuel valves are left open, or until the propellants in the tanks are used up. Let's see how this works. The fuel and oxidizer enter their separate feed lines under pressure from their pumping mechanisms. One goes through the cooling system to the injector, the other directly to the injector, which sprays them into the combustion chamber. Combustion takes place, and exhaust gases, accelerated by the Delaval nozzle, repeat the same pattern of pressures you've seen before, creating thrust. The rocket motor has the simplest design of any known power plant today. With its potential ability to break free of the atmospheric envelope surrounding the Earth, there is no limit to the speeds and distances which man's mind may now dream of encompassing. Only a thorough knowledge of rocket motor operation and rocket motor design will disclose the men who will become the leaders of the future in this wholly new phase of flight through space. And only you who have been chosen to begin this study will have the opportunity to become one of these men. Make the most of it.